Okay, good morning, class. Today we're going to discuss another topic in unsupervised learning. So we've learned two algorithms so far, right? K-means and the EM algorithm in the context of unsupervised learning. So unsupervised learning means that you only have data points themselves without labels, and then you try to group them and try to find the clusters. There actually are a much richer set of problems in the scope of unsupervised learning. And today I'm going to talk about the problem of sometimes known as subspace analysis and also dimensionality reduction, which are arguably maybe even more popular and widely practiced in the field of machine learning. In fact, nowadays, when we hear in deep learning research terms like transformers and encoders, they actually are conceptually closer to this subspace analysis. Although not necessarily it is a dimensionality reduction. Nowadays, people may find the need to do dimensionality explosion to actually blow lower dimensional data into higher dimensional space for specific purposes. So I'm going to talk about some very basic algorithms today, just to get that conceptual principle clear. And then we will present a few algorithmic cases. Okay. So here is a task that motivates this problem many decades ago. Let's think about the problem of a document, text document retrieval and labeling, right? So you are given, say, a text document like this. And one of the, each document, for example, are offered different lengths, right? Some are having, say, 100 words. Some may have a couple of hundred words. So how to compare the different documents, say which one are similar? Right? That actually leads to a representation of documents, which is known as the bag of words. Okay, in the bag of word representation, it's very intuitive. You basically just count the number of words, okay, based on a standard dictionary that all the documents will share. And then you turn this document into a long vector of this counting vector. Okay, so that's a bag of word representation. And then you basically are getting something like this: a table whose columns are indexed by the different words, whose rows are different documents. And then you can basically measure, say, a Euclidean distance between the documents, right? So, and then you can compute the similarities. You can even group documents in this way and so forth. So you can obviously see that there are some problems with this very naive representation, right? In fact, someone want to volunteer saying some potential issues with this very, very straightforward, intuitive representation. Let me open the chart to see whether somebody want to. Does not capture the semantics information. Yes and no, right? The words is semantics. It doesn't capture fully, that's true, but there are no technique that capture everything, but it's the amount of capturing. Word must match exactly to provided signal. Cannot handle semantic similarity and term proximity. Dimension, yeah. Some of these comments are quite sharp. For example, the dimensionality of the vectors is very huge. That's true, because you may have a dictionary that could have 1 million words, right? So therefore, your 200-word document are going to be now represented by a 1 million dimensional vector, which is pretty awkward. And there are then some other qualitative statements which dive into the semantic saliency, basically, of this representation. Let's see, what are what's wrong with the semantic part. For example, here are some obvious problems. One of the problems is called the synonyms, which is poorly captured, in this representation. Consider the two words car and automobile, right? These are two different words. And if just use the word count for representation, you will find a mismatch of the two documents. One carries the word car, the other carries the word automobile. So therefore, the true similarity between the two documents will be much larger than the measured similarity over that representation. Right. We also have some other issues. For example, the polysemy issue. That's the opposite of synonyms, right? For example, if you see the two documents, both contain the word apple. If you don't look at the context, you may believe that they are the same, or they are very similar. But we also know that the word apple, had very different meanings in different contexts. It could mean the fruit, it could mean the company, the iPhone, and so forth, depending on the rest of the word, what they are talking about. Right? So in this case, the true similarity may be smaller than the obviously measured distance based on that representation. I guess basically what this issue is pointing to is that sometimes, we fail to, express, that document or this data based on the concepts, but only based on some surface indexes or maybe dimensions such as the words, right? So how can we, for example, represent the word in the space of concepts? The concept could be a sports topic, a political topic. The White House, for example, could mean the presidency rather than just a White House, right? So these are what we want to capture. So how can we generate this kind of representation and at the same time embed or project our raw data into this new space defined by the concepts, right? So that basically leads to a task. What you want to do is to begin with a collection of unlabeled documents, and then you want to find them, embedding in some space. It can be words, but it can be also some other dimensions, let's say P1, P2, P3, P1, instead of calling them word 1, word 2, word 3, so that the documents are represented geometrically, but also have this conceptual saliency for you to compare similarities, to classify contents, and so forth. Okay, so that's the task. And in fact, as early as in the 70s, people already were studying this problem, and there has been a very well-known technique known as the latent semantic indexing, which gained dominance, in the 90s, in the late 80s, which basically is taking a linear algebraic view of the wording, the document embedding problem and the dimensionality reduction problems I just mentioned. Okay, so there are a lot of different ways of understanding this technique, but the key idea is that instead of representing the document and queries, in a like a t-dimensional space of terms like words, what this latent semantic indexing is doing is to compute algebraically, some vectors, which can create a lower dimensional space. Okay, for example, in this case, you can imagine that I have a 3-dimensional original space, but I could identify 2 vectors in here, which could just define a plane that is lower dimensional. And ideally, these 2 dimensions capture the most salient kind of concepts, in the entire data set. And then you can basically discard the original coordination system and just use this one as the new space to embed your documents. And how to embed is a very, very straightforward linear algebraic operation, right? You dot product it, you basically make a projection and so forth. Right? And the SVD, also known as the singular value decomposition, is the mathematical tool to compute such salient vectors, which can be used as the definition of the axis, in the new space. And these axes are also known sometimes as principal components, and sometimes they were also known, called topics and bases, depending on their use cases. And mathematically, people also sometimes call them factors, although factors have other specific statistical meaning depending on the technique you use. So we're going to today study some of the operations and the computational procedures of this problem. Okay. So let me continue a little bit to motivate on the conceptual level in terms of what's the utility and the value. I think I'm going to just speak very high level. You can read the text in here, right? We know that by using these latent vectors, you achieved hopefully a nice effect of lower dimensionality, because you can choose basically how many factors you need that is sufficient to separate your documents. And there are, of course, a lot of nice motivations about doing dimension relativity reduction. And in the previous slides, the general motivation of factors, as we said earlier, is to capture this kind of saliency in the concepts. And here you'll see a few more examples of what they mean. Okay. Now, mathematically, we need to understand, a few key ideas behind this SVD, the singular value decomposition idea, to turn what we just talked about, in terms of conceptual saliency, for example, in terms of the fundamental directions or dimensions that documents can be projected into without losing information. So these are all very high level ideas, but what do they mean algebraically? So here are some key concepts. First of all, the concept of variance in here plays a big role, because imagine that you find a direct, for example, I'm in such a space, right? And I have a point clouds all over the place. And I happen to find one direction in here on which, if all the points, so basically the points are project to here, and so forth. If, they projected like this, okay, meaning that they are spreading across all these, versus another direction, for example, say in here, all the points are projected to just a small region in here, meaning that this one has a high variance, this one has a low variance. Which direction do you think is more interesting and carry more information? Right, so this is just an intuitive kind of guess, but hopefully leads to our mathematical operation. Yeah, I got an answer, high variance, obviously, right? If you identify a direction like this one, where all the data points are just collapsed into a single location or very, very narrow range, you probably can guess that this dimension is not that useful in spreading data, in tell apart data from each other, right? And but if data are lined in here and they happen to project very nicely to this dimension, that means this is a nice direction, right? So area of variance in the data is something we want to capture, and we want to capture it in the mathematically, explicit way. And then there is also this notion of correlateness. For example, now we know that this is a direction which has a lot of variance. Then how interesting it is about this direction versus, say, another direction, maybe pointing to there. Which one is intuitively more interesting? Someone want to type an answer or shout out the answer? I don't see answer, but I guess you probably can appreciate. Yes, okay, I got the one reply. Thank you very much. Yeah, you probably have a intuition that if I were to find the two best direction of projection, then the second direction is better to be more independent than the previous one, than highly correlated, because of the simple notion of redundancy. Right? Okay, and then basically we are trying to. The problem now turns into looking into the data cloud and maybe identifying some underlying directions, which is not given explicitly in the data, but they kind of describe, the extent of information thread and the extent of redundancy or unredundancy, in the data, right? And this basically defines the problem, that we are going to mathematically solve, right? And these directions that we are talking about refers to what we know as the principal components of vectors. Okay, so much for the high-level discussion. Now let's look at the specific examples. Right. So here I have a data point cloud. Right. It is in two-dimensional space, like in here. Okay. If I will ask you to, say, save some effort and find one direction to, project the data. You are only, allowed to use one number rather than a two coordinate, to express the same data set. Then you need to find a direction that could, express, the data in a more kind of a compressed fashion. How to, you probably already guessed that which is the direction. Well, I guess this might be a good direction, right? If I ask you that I still want you to use two direction, but that direction probably give you the best kind of information in terms of how data are distributed. What could be the second direction? Well, based on the non-redundancy principle, if the first one is already this one, then the second one should be this one. Right? So this is exactly what we want to achieve in our principal component analysis. And the algebraic way to achieve that is actually written in here. Imagine that all the data are centered. Basically, we're going to now first redefine the origin of the coordinate system so that the average of the data points becomes 0. And then what you can do is to make one of this direction. Let's start one by one. Like make this direction, which is of course expressed by a mu, unit vector, okay, indicating the direction. We make this as a unknown variable. It could be pointing here, up here, but whatever it is pointing to, we can always compute the projection of any data point onto this direction, which is computed by this, right? So we're going to basically just compute that projection. Because they are centered, therefore the square of that is actually the variance of the data along that direction. Okay, we're going to take expectation over that. Okay, that expectation can be, of course, computed by just a numerical sum of all the, this square term and divided by 1 minus n, n over 1 over n, right? Okay, so now we get down to another problem where we can maximize the variance computed in this way. So this mu transpose times x transpose times u is actually the entire variance that you can compute from data. By the way, this X is the data matrix. It's a matrix of all the vectors. Each of them correspond to a document. Okay. And we know that X times X transpose is also known as the covariance matrix of the data. Therefore, you are literally just looking for a projection direction mu, which achieve the following effect by left multiplying the covariance matrix with mu transpose, and the right multiplying the resultant vector with another mu, which actually leads to a scalar. We want to maximize this quantity. Okay. So in the end of the day, this problem is about solving a direction of mu that maximize the variance of the data projected to this direction. Okay. And that leads to a very, very standard optimization problem, constraint optimization problem. So we maximize this, and this is the constraint of the mu to avoid basically a trivial maximization result, because you can make the size of the mu infinitely big, so to achieve the maximization in here. But that's not meaningful because the information of the direction is lost. Therefore, we set the direction vector to be of unit length, and then only the orientation is going to be a variable. Okay, and solving this is is a pretty standard problem in constraint optimization. You build a Lagrangian. Here, lambda is what is known as the Lagrangian coefficients, a Lagrangian multiplier, and then you take a derivative of the grand Lagrangian over the mu, and then you get to this equation in the end, which gives you the solution. Okay, so if you look at this, you can probably see already this is a linear system, and the solution basically can be achieved by finding what is known as the eigenvector, of this covariance matrix. Okay. Okay. So let's study again. I'm not going to use this lecture to discuss linear algebra. Therefore, if you have some gap, to the concepts of eigenvalues and the eigenvectors, I would encourage you to read review some of the college algebraic books, or go to the TA on office hours to get some clarification. But here, I just want to state a few key properties of the eigenvalues and eigenvectors. Okay. So here, this is the definition of the eigenvalue V and the eigenvalue lambda and the eigenvector V. Okay, and the vector is to avoid triviality, it should be a non-zero vector. Okay, and also the lambda, the eigenvalues should be a real number. Okay, so this is just an example of the definition of a eigenvector and also its eigenvalue. And the next question, basically for any matrix, square matrix X, you can get it corresponds to a set of eigenvalues and eigenvectors. Okay, now how many eigenvalues and the eigenvectors you can have at the most? I mean, how many non-redundant ones? Well, there is a very simple mathematical proof which will show you that for a matrix with rank K, with rank M, you get at most M distinct solutions to this linear system. Therefore, you have M, at most distinct eigenvalues and eigenvectors. Okay, so this is just, I'm not going to prove it, but yeah, someone actually gave an answer already. That's great. Yeah, but if you are not familiar with this, you can now take it as a fact and then figure out why it is so, in your after class effort. There are some other important properties of eigenvalue and eigenvectors. One of the most important properties that by definition, different eigenvectors are known as orthogonal to each other. Okay, meaning that their dot product always leads to a 0. Okay, and in this case, you have two eigenvectors. Therefore, these two must be different, and they are orthogonal to each other. Let's see what else I need to cover. Yeah, it's already said so. All eigenvectors. Oh yeah, there are some special cases. If your matrix is real and symmetric, then it is guaranteed that your eigenvalues will also be real. Okay, that's a nice property to know. So symmetric matrix and the real matrix makes the condition better. And the condition can be even better if your matrix S is called positive semi-definite. If your matrix is a positive semi-definite, then your eigenvalues will be not only real but also non-negative. Okay. Well, it's actually very easy to define what is a positive semi-definite, but I'm not going to spend time here. You can in fact, it's defined in here, but you can discuss with TAs if you want in terms of exactly what it entails about the factorization of the matrix. Okay, so now we've got quite a few concepts already, right? The eigenvectors, of a matrix can be computed. And it is actually known as the principal components in the context of our, LSI analysis, latent semantic index analysis. And the first principal component is actually guaranteed to have the greatest amount of variance in the sample. Okay, so basically these principal components can be ordered. Remember that in our point cloud we see just now, we basically make this the first, and then this one is the second. So when we actually do PCA, for the input covariance matrix, you always can rank, the resultant M eigenvectors, and then after the rank, you can, have the following property guaranteed that the first PC is the one carrying the greatest amount of variance. The next PC carries the next amount of greatest variance after the first one. Basically, when the first one was removed from data, and then the second one will carry the biggest variance. Okay. And I think there isn't anything. Yeah, there is another concept you want to remember, which is the least square view. The PCs, the principal components, is a series of linear squares fits to a sample. Okay, which basically what I'm saying is that if you want to fit the data point using one dimension, then you can the first dimension is basically the least square fit, because remember our this is the least square. If here you don't see that so clearly because the data are centered, but if your data are not centered, you actually will see that it is mu times right. So this is by definition the least square fit of the mu, right? And once you fit that and you subtract basically the projection on mu from the data, and then you find another least square fit of the mu, you get the second principal component. So that basically tells you the correspondence between PC and also the least square fit of the direction. Okay. All right. So then, because the principal components are all ranked, you can now have a option to choose, out of the m possible principal components, how many I want to use to represent the data. Why this problem is interesting? Because remember, to compute PC, you begin with a matrix of a C, the covariance matrix. And what's the size of the covariance matrix? Well, it is n by n, right? N being the number of data points. And if you have a very large data set, say a few thousand data set, then you could, and if they are non-redundant and therefore full rank, then you can potentially get a few thousand such principal components, which is probably too cumbersome for you to carry all. And if you just plot their eigenvalues, remember the eigenvalues correspond to the amount of variance in that particular direction. You actually could see how much variance is carried in each direction. And typically people observe that the distribution of the variance drops very quickly, across all the principal components. Maybe after 10, the whole thing will be just residual. Maybe 95% of the variance is already captured in the first 10 principal components. Therefore, you can basically cut from here. Okay. So this plot of the eigenvalues could help people to find maybe a cut or a threshold of identifying how many PC, rather than just do a random guess. Someone may choose to cut from here, for example, where you see anything after that start to drop very slowly, but before that you see a much higher number. Okay, now having talked about the PCA, let's move on to another concept called singular value decomposition. So remember, in PCA, you started from a symmetric matrix C, which comes from X times X transpose, right? And in the field of information retrieval or in text mining, people are not comfortable thinking in the form of the C, the covariance matrix, because it's very abstract. You get a sense of variance and covariance among data points, but the original meaning or ingredients of the data somehow get lost. For example, the frequency of the word and the strength of the word and so forth. Therefore, people are more comfortable just thinking about the X, which is also known as the term document matrix. So here are the terms, here are the documents. So every document is say a vector, something like this. Okay. So they want to start from here, and then we can use a technique known as the SVD to also decompose them into a sequence of matrix products. Okay. So for example, given a matrix, which is n by n. Okay, so this is a rectangular matrix, and let's say it has a rank R. Rank R is something that is not very obvious from the data, but when you compute the singular value decomposition, you actually will see how many non-zero eigenvalues you will get, and that usually correspond to the rank of the matrix. So it can be written as a U matrix, which is m by m, is a square matrix, times a m by n diagonal matrix, and times a n by n rectangular matrix, square matrix again. Okay, so this is known as the singular value decomposition. And this U and the V matrix are very interesting in the sense that maybe I should just draw it in here. So this equals to, maybe a this matrix times this matrix and times something like that. Okay. Okay, so this U matrix in here is made of many columns. It turns out that the columns in this matrix correspond to the orthogonal eigenvectors of this matrix, A times A transpose. Okay, and the columns in here correspond to the eigenvalues of this covariance matrix. It is the A transpose times A rather than A times A transpose, which is a n by n matrix. And then the eigenvalues, okay, of the lambda in this has a relationship with the eigenvalues in here, like this. Okay, so the sigma, which is the values in here, basically correspond to the root mean square. Is square root of the eigenvalues of these matrices. Okay. By the way, this matrix and this matrix have the same eigenvalue. Okay, and you can prove that by some algebraic operations, and therefore, their square root is actually corresponding to the numbers in this sigma matrix. Okay. So that basically, get us, the SVD theorem. Okay, for the S to be a square matrix with m independent eigenvectors, then there exists an eigendecomposition, of this. This is really what we have in the PCA. And they have, again, this ranked list of eigenvalues. But, they leads to, the SVD in a close relationship where, as I said just now, the columns in the left matrix and the right matrix correspond to basically the PCA of the full square matrix resultant from the A times A transpose or A transpose times A. And then the eigenvalues of the rectangle matrix is just a square root of the eigenvalues of the original matrix. So how that actually happened? Okay, remember everything starts from here, right? So this one leads to a a singular value decomposition. A PC principal component analysis is a matrix decomposition of the square matrix. And if we do this, right, V is the V matrix is basically a matrix of column vectors, which are the eigenvalues of this guy. And then if I do something like this, let me see if I can do that. Okay. Anybody realize that I'm basically just making a trick of inserting a identity matrix in here. Here, I introduce a matrix called the U, okay, which is a orthogonal matrix. If it's a matrix of eigenvectors, which are unit length vectors orthogonal to each other. And then I basically introduce U transpose times U, which actually leads to identity. And therefore, these two square root of the sigma can actually be multiplied again to recover this mu. So this identity is basically straightforward. And then if I look at this part and this part, you probably can see that xt times x equals to v right? And that basically leads to this, where the rectangular matrix can be now expressed as a product of three matrices, mu and sigma and v. And then what is sigma and what is u and what is v are pretty straightforward, from this definition in terms of why they are the eigenvalues and eigenvectors of the original square matrix of covariance. Okay. Is there a difference between singular? Okay, so Daniel already answered the question. Any other questions at this point in terms of the relationship between SVD and PCA? It's a little bit confusing, but in fact, many people don't tell the difference between a PCA and a SVD. PCA is a brute force kind of PCA is basically working on the covariance matrix, and the SVD works on possibly a rectangular term document matrix, right? But then algebraically, PCA is to directly solve a eigenvalue problem because it is a square matrix, and the eigenvalue and the eigenvector problem is straightforwardly defined. And the SVD, the solution of SVD requires, to turn back to the PCA in terms of solving the eigenvectors and eigenvalues. Okay. But indeed, they are very, very similar, and in terms of the operation needed to get to the eigenvalues and eigenvector. So with that, let's move out of the algebra, which is a little bit painful, and look at how this problem can, how this technique can be used now to solve a real problem. Okay, so here is an example of a data set with this many documents. Okay, each of them basically is represented now by a term frequency. So this is known as the term document matrix. Oh, by the way, you may be a little bit confused by X and X transpose. Yeah, this is a confusion term. Sometimes people, use the row to list all documents. Sometimes they use the column, but that's not really a big deal because they all lead to the same eigenvectors. So in here, let's first inspect maybe these few documents. You'll probably notice that there is a column where there are no kind of instance of any of the terms given in the list. Okay, that caused this matrix, which has originally how many columns? 8 columns, to have effectively only 7 columns. Okay, so this is a rank 7 matrix instead of a rank 8 matrix because this particular column, has all 0 elements. Okay, and then we can do a SVD. Let's imagine that this is a X matrix, or maybe we call it a matrix in here. This is a matrix, and it leads to a U and a sigma and a V, which can be numerically computed. And again, in MATLAB, or there are many libraries just does this for you in a single command line. Now let's see, usually after doing this, people would first inspect these eigenvalues to see how much each of the eigenvectors is preserving information. The larger the magnitude, the better. And also you can use this accordingly to chop off what you consider to be less essential directions or eigenvectors so that they are left out. So in this case, you can imagine how to choose a low rank. In fact, you can choose any of either the low rank, based on a numerical justification, basically by setting the smallest r minus k eigenvalues to be 0, you are going to get an approximation to the original A matrix. Right? So this is what happens. And then you are going to get a reconstruction of the A matrix, which only based on the first k eigenvectors. Okay, so this is actually a reconstruction. And you can actually measure the distances between the original matrix A and this one. That actually gives you a quantitative assessment of the quality of approximation by this low rank approximation. Okay. And it turns out that the distances between these two, okay, can be measured by what is known as the Frobenius norm, which is basically the Euclidean distance between two matrices. You can view all the numbers in the matrix as a coordinate and then calculate the distance between the two matrices. Okay, and it turns out that if you have a k rank approximation to the original full matrix, then the error is exactly defined by the k plus the case, well, the next eigenvalues, after the k eigenvectors. So it's pretty neat. That's why when we look at all the numbers below, we actually could even quantitatively measure, the approximation error. So in this case, you can imagine that we can now, see, a very convenient way of reducing dimensionality. And this is actually also what is known to be a major goal in LSI, the latent semantic indexing. Say, starting from a huge, say, matrix of 50,000 documents, and maybe 50,000, say, terms, and maybe 10 million documents. Okay. Of course, this matrix shape isn't representing that. In fact, here we have a way bigger kind of number, but in here we have 50K terms, which are still quite big. Right? And then this term document matrix now gets a SVD, as we just see before. And here is how the SVD would give you, right? They give you, a ranked list of all the eigenvectors. And you can stop basically from somewhere, say from here. And then what you get are two smaller matrices, which are totally up to your control. You can basically choose this to be K. Okay. And then what you get is, a submatrix in here, which contain only the first, K eigenvectors. And in here, you have also the first K eigenvectors in here, okay? And this subset of the eigenvectors and eigenvalues will be able to reconstruct this original input matrix A. And we know that the error is defined by the sigma plus 1, okay? And in this particular case, how do we make a correspondence of the original document in here, okay, versus the document in the projection space? Okay, actually, this is how it works. If you look at this D matrix, okay, here you are going to get by the way, it's a K times N matrix. N is still basically the total number of documents. Therefore, each document now has a correspondent in this matrix. but it is not a lot shorter vector. Okay, it is only of dimensionality k. Okay, and this one corresponds to now the new representation of the document. Okay, that basically achieved the goal of dimensional reduction. Your document, which were originally 50k dimensional, becomes now a k-dimensional, much shorter vector. And then these k vectors in this matrix U actually carry semantic meanings. They usually correspond to, what is known as the topics, in this entire corpus, which allows you to spread, to define the subspace, the latent space on which your document can be projected into. Okay. So what I just talked about, in LSI, is also known as subspace analysis. Before I move on, I just want to have a brief kind of elaboration of this technique, subspace analysis, so that you know that it actually corresponds to something even beyond SVD. For example, in here, in the past several decades, there has been independently a number of different techniques developed for analyzing data without labels and making projections of the data into some space. It turns out that they can be all unified under the concept of subspace analysis. And the only differences between all these different techniques, is actually the very numerical conditions or characters of this T matrix, lambda matrix, and also the D matrix. We've seen, for example, LSI already, right? Which basically says that these two matrices are arbitrary. They are just the eigenvectors of some input matrix, and this one can also have arbitrary real numbers. But if you make a constraint, for example, if let's say this particular matrix is constrained to be just the 0-1 matrix, or the so-called one-hot matrix, meaning that every vector here, okay, say this vector here, is a one-hot vector, meaning that only one dimension is going to be 1, and all other dimensions is to be 0. Then, what this vector is achieving is to assign, that particular document into one of the K clusters, right? You can imagine that the second, maybe this is one hot in here, and that one is one hot in here, and this one is one hot in here. Then it basically achieved the goal of clustering the data, into, some clusters. And then the vector in here could be understood as the cluster centroids, the average of the points of those clusters. And then the analysis becomes a subspace, it becomes a clustering analysis. So in a sense, you can solve the clustering problem, like we have two algorithms, the K-means algorithm and the EM algorithm. Now you can have a third algorithm where you do a constraint optimization, that you define such 3 matrices, okay? And you constrain the matrix to be of certain property, such as the 0-1 matrix property. And in here, you have some numerical correspondence of making every vector being an average of the points resultant. Right? So this is a way of solving that as well. Although rarely people use this approach, because this is a little bit numerically too hard to solve. There is another technique known as the topic models, latent semantic indexing in the probabilistic domain, which actually requires the vector in here to be now a stochastic vector and the whole matrix to be a stochastic matrix. What does that mean? That means that every vector in here is a vector of positive, non-zero positive numbers between 0 and 1, and the summation of that sums to 1. Okay, so that means that the probability of basically this particular document being in every topic, in every dimension. Sometimes you can also make this matrix sparse, meaning that it's favored to have a fewer number of non-zero elements in here. How few? Well, it depends on the strength of your regularization or constraints. But that's actually another free parameters people can tune. But the resultant results is also known as the sparse coding. You are going to now encode every of this document into a sparse vector. Okay, so these are already 4 examples of subspace analysis which were developed separately in different contexts. But using this matrix expression, you can basically view them to be variations of a pretty straightforward single concept that projects the data into latent space. Now let's look at how the example that I just showed proceeds, right? I said that given this turn undocumented matrix, you do SVD and you get this U matrix, this lambda matrix, and also this V matrix. And after inspecting the eigenvalues in here, I may decide to pick only 2 eigenvectors. Therefore, everything else is left out. Okay. Then what these 2 eigenvectors can be used is to define now a new space of only 2 dimensions rather than the original space of many more dimensions. And then we can make a projection of all those data points into the new space. And here is what a projection look like. Okay. These actually are the original articles which produces this turn document matrix. And now you can see this projection resulting from the SVD and the low rank approximation. There are 2 dimensions only. Okay. And here you see 2 type of points. One is those M points. Okay. The M points are basically corresponding to these guys. Okay. It is basically the new coordinates of the original documents, in the new space. Okay. And you can see that one interesting thing is these documents do not go all over the place. They are, for example, there are no documents in here, right? They're kind of aligned in here and in here, which is already displaying some maybe nice pattern of clustering effect in the latent space or in the topic space. Then there are also, words, in here. These are some other projection. What are these? These are basically these numbers. Okay, it is the topic vector, but now expressed as the weights of every term, every original term in here, in this new topical space. Every word, for example, this word, say, matrix, right, could have different weights in these 2 topics. One has a weight of 0.3, the other has a weight of negative 0.4. That means that this word matrix is strongly contributing to topic 1 or eigenvector 1, but not eigenvector 2. Right? So now look at the pattern of the words. You kind of see that in here, there are names like words like I cannot even see it. Maybe I can blow it up a little bit. You can see disease, for example, this word, and another word called blood. Maybe you can already guess that this particular dimension represented by a 1 eigenvector correspond to maybe a disease to the blood and something. And in here we have words like depressed and I don't know, culture. Well, that may be another disease which are more psychological, right? So that's why people say the LSI automatically discovers semantic topics, just by looking at the word frequency or word weights in each of the resultant eigenvectors. And that's exactly where you see here. One is more like a blood disease. The other is more like a mental disease. Okay, and then the documents can be grouped accordingly or projected accordingly. So that's one utility. You visualize the data now by eye in a two-dimensional space. And this is achieved by reducing the dimensionality of the original data down to a two-dimensional space. And then you can also use the projection to more saliently identify clustering or grouping patterns of the documents, and also to even identify the intrinsic topics existent in the corpus. Okay, so that's one major application of LSI or SVD. Another application is to use what we just have as a tool to compute queries and to, for example, classify the label of a incoming new article. For example, I have a query which leads to the following original word embedding, the backward word representation. Then you can multiply this Q vector with the U matrix. Remember, the U matrix now have only two major eigenvectors. And then you need to normalize it by multiplying an inverse of the eigenvalue matrix so that they become magnitude-wise comparable to the already projected documents in here, because they all basically have the matrix in the eigenvalue weighting already done when they are projected. So then you get now a new expression of the input query, which is in here. Okay, you have a bunch of representations of the original documents, and then you have this new one in here. And what you do is to just compute say a pairwise distance, or maybe a cosine value in this case between this vector to any one of the other 8 vectors in here. And then you can determine which one is the closest. I guess this one is very close. Probably you want to match this query to that document, right? So geographically, you can also see that. Not geometrically, you can see it, right? So among all the documents in here, M1, M3, M2, and so forth, your query basically lands you in here, which is closer to what? I don't know. Yeah, there is a M2 in here maybe that is closest to this one, I hope. Okay, so that's another application. You compute, use the new eigenvalues and eigenvectors to compute projections of the query into the topic space, where you can make predictions of the title and topics label of the query documents. Okay, I think that's the end of the major bulk of the material today. I talked about what latent semantic indexing is and what it can be used for, in DR, in correlation analysis of query documents, and all these other things, noise reduction and exploitation of redundant data is simultaneously achieved just by looking at the projected data into the latent space. Right. One of the challenge of SVD or PCA in general is the computational complexity. We need to now do single value decomposition, and we know that it is a n-square operation where n is the dimension of the matrix. Right. So if you have a very big term and document matrix, that n can be very, very big, and that could lead you to some computational challenge. And that's also why a later technique known as the LDA, latent differential allocation, or probabilistic talking model was invented, because in there you can use a EM procedure to incrementally learn the topics without factorizing the whole matrix. At least that's one of the convenience, for that new technique. Okay, we have another 15 minutes. I'm not going to read the summary again. You can take it home and review it by yourself. But I want to say a few extensions of this technique, just for our maybe knowledge and information. Actually, before I do that, any questions so far from the materials presented already? Any questions so far regarding the TCA and SVD and the LSI, latent semantic indexing? Nope. Okay. Then let's look at we talk about the text in the NLP applications a lot. In fact, in the image domain, computer vision domain, we have exactly the same problem, maybe even worse, because an image is represented by pixels. Therefore, every image, is represented by a huge matrix of pixels, which can be linearized into a very long vector. Okay, where n could be easily tens of thousands, if not millions. And here, people also are facing the dimensionality bottlenecks because images are just too high dimensional and hard to manipulate. And then people ask, right, how can we group images, and or how people mentally group images, right? For example, in here, does our brain store all these pixels literally, or we kind of discover patterns from the images? For example, here you can probably see that there are, maybe left side views, maybe middle views and right side views and so forth. Maybe that's the way we, recognize images. I don't know. But the point is that how can we, computationally, or numerically, discover such groups of images? It turns out that the technique used is very similar to what I just described, in the LSI. Okay, here people also raised a few other interesting geometric points for people to consider. One is, what to preserve. After you make the projection, in addition to maximizing variance, for example, or achieving non-redundancy, there is yet another angle to look into the problem, which is my projected data preserve some of the key properties that I have in the original data? For example, here, this may be a original data, which is three-dimensional, right? And then I want to project them into a two-dimensional space, or vice versa. I can project from 2 to 3, to make a dimensionality explosion. When you make this projection, you can see this shape between this and that can be very different after the embedding. But what is the important thing to be preserved? So here, one of the interesting things to preserve is the neighborhood distances between points. If you and me were neighbor in our real life space, then when we will project to another space, time or of space, maybe we still want to be neighbors. That means this projection is preserving some code information. Right? So this could be what the image people want to do. Another preservation is called the information preservation. It's about representing the data not as its raw surface value, just as a pixel value coordinates. I want to use a model to, for example, this whole line is generated by a linear function parameterized by theta. Okay, and maybe that other line is preserved by another linear function parameterized by theta prime, right? And instead of asking the line to be close to each other, I may ask the theta to be close to each other. That means the information content or meaning of the surface data gets preserved. So that leads to some other type of preservations. Okay. So let's continue on how to make this embedding. Using some additional ideas in terms of our what we see already in SVD. What they want to achieving here is to be more explicit of preserving the data dependencies in the training data. Remember, in our PCA, we didn't actually look at the data points point to point to worry about preserving their distance, right? We were basically talking about reducing, for example, this quantity. Is the projection of the data onto a direction and then minimize their variance. We didn't talk about the data-to-data relationship. But in here, what if I want to achieve a projection which preserve me some data property? So that basically leads to a extension of the technique we just mentioned. Departing from here, we can actually expand the notion of the covariance matrix. The covariance matrix is actually capturing some kind of affinity between the data points, right? But you can also use some other method to compute the affinity. For example, you can just replace every entry in the theta in the C matrix to be just the pairwise Euclidean distance between the points. This is known as the MDS, okay, the minimum description length, something like that. I forgot the exact name. There is another technique to fill in the matrix A, known as the geodistance. So in this case, you are not going to be, relying on, the entire kind of distance, between all points. You basically are only going to pay, or maybe you should, I should say that you pay stronger attention to the data points closer to you, okay? And also maybe ignore the numerical values, but more on the operational values. For example, after computing the pairwise distances between points, do I have a graph? Yeah, I have a graph here, right? You can basically, suppose I give you this graph, these data points, you can compute a graph, called neighborhood graph, based on all the pairwise distances between data points, okay? And then you can do, a shortest path kind of operation on this graph to compute what is known as the geodistance, the number of steps you need to walk to the other data points. Okay, so this is not a Euclidean distance, but a operation distance of path length, on a distance graph. Okay, and then you can basically put this number into the C matrix and get you another type of decomposition. Right? So basically, the art of embedding is to really be creative about this C matrix, either using Euclidean distance or geodistances, and there are many other kernelized and other embeddings people come up with by different operations, which I'm not going to talk too much about. But at the end of the day, what all these are trying to discover is what is known as the manifold. In the manifold, it's a topological space where data are only treated Euclidean locally. For example, here we have a manifold, right? And in this manifold, the distance is defined in a locally geometric way, but not a global way. For example, this point and this point are considered to be far because they need to walk across the entire kind of wheel to get to the other point. But on the other hand, data points in here, can be very close to each other. And you cannot just cross a space, to draw a direct line, to reflect the distance in a out of the manifold space. So if this is a property you want to preserve, for the data, or in other words, you believe that the data is a manifold rather than a data cloud, then the distances function I just described is one of the effective way of achieving that kind of embedding. They preserve, the manifold properties of the data. And these kind of properties are often very, very useful. People, one of the famous example, I don't know whether I have it or not, is known as, the Swiss rule example, right? I think people are very good at picking this continuity of data in the data space, that this row, for example, is defining a subspace where data lies, right? And you don't basically naively claim that this point and this point are very close to each other, simply because in the higher order space, they look close. In fact, they are very far from each other by this amount, right? Because they live in a submanifold. Right? So in image, people believe that in computer vision, people believe that, for example, the brain picture, the head pictures I just mentioned in here may actually be, entities that is living in a manifold instead of living in the Euclidean space of pixels. And therefore, to embed them to the proper lower dimensional space, you want to preserve this kind of manifold property, such as local geometry, local Euclidean, and also path distance and so far, rather than preserving the straightforward, original high dimensional pixel space distance. Okay, so I think that's pretty much what I want to say. So the technique of PCA, or the technique of singular value decomposition, can be used to achieve now one more goal beyond DR, beyond retrieval. They also could be used to recover submanifold, in high dimensional space with a low dimensional representation, so that you can start uncovering more kind of salient grouping properties and dependencies between the data point that is in the submanifold space. Okay, time is up. There are some additional examples I didn't go through, but you can see these fun graphs, telling you how such embedding can unroll the data into a more intuitive form and making them more easy to compute and cluster. And there are other applications of image imputation and so forth using very simple embedding technique. Okay, so with that, I think I'm going to finish today's lecture. Any questions in the last minute?
I had a question. It seems like PCA is kind of a sub problem of SVD. Like you get the principal components for free when you do SVD. So yeah. When do you use one or the other?
That's a good question. In myself, many people, including myself, probably get confused. PCA in a narrow sense literally means that you define that matrix of interest to be the covariance of the data, and then you get principal component. In a sense, SVD is a lot more generic. They basically literally refers to the technique of decomposing any square matrix or any rectangular matrix into a product of other matrices, right? And with singular values corresponding to singular eigenvectors corresponding to certain, design matrix. Yeah, so I would say SVD is more general, and the PCA is a special case. Yeah, right. But I guess sometimes it's a little bit trickier to stick to such a very strict kind of hierarchy of definition, because in that case, the new technique I just mentioned about the manifold learning isn't really a clear instance of SVD, right? It is also coming from a design matrix that is not covariance, right? So I wouldn't basically organize all this technique as a hierarchy. One is at the root, the other are just special cases. It's a graph of different techniques. They are related, but it's not that one subsume the other as a special case, not always.
Okay, thanks.
Yeah. Any other questions? All right. Then that's the end of today's class. We'll see you on Wednesday.